a quick little video about errors in induction and how they can be used to prove some pretty erroneous results. So here's an example. Here I think this one is pretty obvious that this is false. So for all integers n that are greater than or equal to 1, n is odd. Obviously that's false, but let's try to prove that by induction. So the base step, n equals 1, since n is odd, the base case is true. That one is easy. Let's do our strong inductive step. So we're going to assume for some k, for all I between 1 and k inclusive, so including 1 and k, that I is odd. So the first k numbers from 1 up to k are all odd. And we want to show that k plus 1 is odd. Okay. And remember this. Remember that we're assuming that all numbers from 1 to k inclusive are odd. K minus 1 is less than k. So we're going to assume this guy is odd. So k minus 1 is odd. So we can write k minus 1 as 2a plus 1. All right, let's add 2 to both sides of this. And we get k plus 1 is k minus 1 plus 2, which is 2a plus 1 plus 2, which is, if you factor out a common factor of 2, it's 2 times a plus 1 plus 1. This guy is indeed an integer, so I've written k plus 1 as an odd number, 2 times a plus 1 plus 1. So I guess we've showed it. We've showed that every number from 1 onwards is odd. Obviously this is false. Where is the error? So maybe pause the video now and see if you can find the error for this induction. All right, now that we're back, we have to be a little bit careful here. When we're saying k minus 1 is odd, well, that really isn't in our set when k equals 1. K minus 1 doesn't fit this. So that's kind of the key here. This k minus 1, this guy isn't in the natural numbers if we picked k to be 1. So what this is saying is we have to do a special case when k equals 1. So really we'd need to do a special case. Obviously this is going to be false. This is where the error is. Special case for k equals 1. Okay. So when k equals 1, k plus 1 is 1 plus 1, and 1 plus 1 is, of course, 2, and if you want, you can write this as 2 times 1 to show that this is indeed an even integer. So the argument is not true when k equals 1. Our induction falls apart. And that's why it's important to be careful about your special cases here. Make sure that anytime you assume that you're taking parts of your domain that are less than something, if you're subtracting 1, make sure you can actually do that for all the numbers. And the cases you can't, you just have to do it for a special case. Again, when k equals 1, k minus 1 is out of our domain. It's 0, so we can't use this argument. We have to do a special case when k equals 1. So we do the special case for k equals 1. We find it's not true, so our induction falls apart. Of course it does. Of course not every integer 1 and greater is odd. That's ridiculous. So this is just a little example to say, just make sure that you're careful when you're doing inductions, especially around special cases.